This is AP Calculus, Notes, Section 3.1. We are going to learn the product rule. This is the product rule for derivatives. Before we get into that, let's remind ourselves how we would find the derivative of a product if we didn't know the product rule, what we've been doing so far. So we're going to rewrite this function without the parentheses using the distributive property. And the directions say find the derivative and then explain what this derivative means. So to rewrite this, we're going to distribute the 2x to each of these terms. It's going to be 2x cubed minus 4x squared plus 2x. I'm going to distribute the minus 3 to each of these terms. Going to get a minus 3x squared, a plus 6x, and a minus 3. I've got like terms of a minus 4x squared and a minus 3x squared. 2x cubed has no like term. I've got like terms of a plus 2x and a plus 6x. And the constant minus 3 has no like term. So we wrote that as a cubic function. Now to find the derivative, remember f dot, that's Newton's notation. We're going to multiply the 3 times the 2 and subtract 1 from the exponent. So that would be 6x squared. Multiply the 2 times the minus 7, subtract 1 from the exponent. Multiply the exponent of 1 times the 8, subtract 1 from the exponent. X to the 0 is 1. And the derivative of a constant, negative 3, is going to be 0. So let me redo this. We're supposed to rewrite the function. We did that. We're supposed to find f prime of x. We did that. And then we're supposed to figure out what does this equation represent. F dot of x, or f prime, represents the slopes of all the tangent lines of f of x. This is how we would do this problem. But now we have a way that we can do this where we don't have to multiply this out. We can just find this derivative directly. And in some cases, you might still want to multiply this stuff out and then find the derivative using the power rule. Two men, Isaac Newton and Gottfried Leibniz, are credited for developing the study of calculus. In 1673, Leibniz published an article where he derived what is known today as the product rule of differentiation. Just a reminder, differentiation is just a different part of speech for the word derivative. Product rule means that you're multiplying two functions together. A function defined as part of the term has a variable, and then another part of the same term has a variable. Let's write this rule together in the box below. So if this was truly Leibniz, this is the way Leibniz would write it. He would say, let's say if h of x was equal to f of x times g of x, then the derivative of h of x with respect to x would be, you take the derivative of the first function, that's the derivative of f with respect to x, and then you multiply that by the second function. Then you add to that the first function times the derivative of g of x with respect to x. If Newton was doing this, this is Leibniz. Newton might write it like this. If h is equal to f times g, where h, f, and g are all functions of x, then f dot, pardon me, and h dot is equal to the derivative of the first function times the second plus the first function times the derivative of the second. If Lagrange was writing this, he might say if h equals f times g, then h prime is equal to f prime times g plus f times g prime. Those all say the same thing, just using different notations. This of x that you see in the first one, that could be used in any of these. And going the opposite way, we could strip away the of x here in Lagrange or in Leibniz notation. It has the same meaning. The reason I took away the x's down here is just to make it more clean. You can more easily see what the product rule is. So let's see how this works. We'll use Lagrange notation for this. So the derivative of f prime, we take the derivative of the first function, so that's 2x minus 3, we gotta take its derivative, times the second function, x squared minus 2x plus 1. We add to that the first function, 2x minus 3, and we multiply times that the derivative of the second function, the derivative of x squared minus 2x plus 1. Here's the symbol for we're going to take the derivative. So what's the derivative of 2x minus 3? It's just 2. It's only one term in that derivative, so we don't need to put it in parentheses. Derivative of the second function is two terms, 2x minus 2. So I cannot leave it like I just wrote it, because we are multiplying this whole thing times this binomial. So this needs to be in parentheses. Now, if this was a free response question, you would be free to leave this as your answer. But if it's multiple choice, they are unlikely to leave it like this. So we have to multiply the 2 times the trinomial, distribute this stuff over here so we can get this so we don't have parentheses. So f prime of x would equal 2x squared minus 4x plus 2. If we distribute the 2x here, we're going to get 4x squared minus 4x. If we distribute the minus 3, we're going to get minus 6x plus 6. And then as far as like terms go, I'm just going to highlight what the like terms are. So we can put all of this together. My blue like terms would be 6x squared. My reddish like terms would be minus 14x. And my purple like terms would be plus 8. Now you might be wondering, what is the point of using this product rule if after you find the derivative, you still have to distribute all this stuff and multiply it out? Wouldn't it be easier just to distribute this stuff to begin with and then multiply it out? The answer is probably. For this problem, there's nothing inherently better about using the product rule. However, sometimes you can't rewrite a problem as a polynomial. If you look at this next problem, we are supposed to apply the product rule, and we're supposed to find the slope of the normal line. So we have g of x, and hopefully you can see here that this cannot be written as a polynomial. There's no distributing here. We have two distinct functions. We have x and we have sine of x. So if it helps, oh, something else I wanted to mention up here, which I forgot about, I apologize. This step right here is not required. That step being showing that you're going to take the derivative of the first function in the second. You can go directly to finding the derivative of the first function and find the derivative of the second. What I wrote in purple is an optional step. Sorry for not making that clear. All right, so for g of x, we need to find the slope of the normal line. Let's first find the slope of the tangent line. To do that, we got to find the derivative. We'll go with Newton. We'll go with Newton's notation. F dot of x equal to, we take the derivative of the first function. The derivative of x squared is 2x. We multiply that by the second function. Then we add to that the first function times the derivative of the second function. The derivative of sine is cosine. Had we not known the product rule, there is no way for us to do this short of using a calculator. This cannot be simplified. You could factor an x out to the front from each of these terms. It's the best you could do. It's not that helpful. We're supposed to find the slope of the normal line of g of x when x is pi. So we got to find the slope of the tangent line first. So g dot of pi, that's going to be 2 times pi times sine of pi plus pi squared times cosine of pi. Just a quick review. Pi is on the negative x-axis. That'll be over here. Over here, we would say x is -1, y is 0, and r is 1. Sine of pi is y over r, so that would be 0. Cosine of pi would be -1, because that's x over r. This first term is going to give us 0. This is going to give us a negative pi squared. That is the slope of the tangent line. Question asks for the slope of the normal line. The slope of the normal line is the negative reciprocal of this. So we're going to write the slope of the normal line to g of x when x equals pi is, if we take this, if we change the sign, it's going to be positive, but we reciprocate it, it's 1 over pi squared. Slope of the normal line to g of x when x is pi is 1 over pi squared. All right, that concludes the first video for these notes. This is an introduction of what the product rule is and how when you have to apply it and when you could apply it. This is video 1 of 4 for section 3.1.